Hello and welcome to another geometry read-along. Today we have Chapter 3 of College Geometry, a problem-solving approach. We're going to open up Chapter 3 and run through Section 3.1. This chapter deals with perimeter, area, and volume. So, a little history for you. Archimedes, who lived between 287 and 212 BC, is considered to have been the greatest mathematician in antiquity. One of his discoveries was that by using appropriately dimensioned cross-sections, a solid cone and a solid sphere placed 2 units from the fulcrum of a lever, so that's these guys down here, 2 segments away from the fulcrum, would balance a solid cylinder placed 1 unit from the fulcrum. Because the volume of the cylinder and the cone were known, he then found the formula for the volume of the sphere by using a law of physics. Right? If they're all of uniform density, right, then you can directly correlate their volumes to their weights, which are equal based on the lever, or rather double. Right? Pretty clever. Speaking of clever, we have a new problem-solving strategy in this chapter: use a model. The use a model strategy is useful in problems involving figures. A model may be as simple as a paper, wooden, or plastic shape, or as complicated as a carefully constructed replica that an architect or engineer might use. This is those, miniature versions of buildings you often see carefully constructed to scale. So, the initial problem. Describe a solid shape that will fill each of the holes in this template, as well as pass through each hole. Okay? Getting through the hole is easy. You want to completely fill it. But the trick is you want one object that can do all 3 different shapes. So in general, the use a model strategy may be appropriate when we can use physical objects to represent the ideas involved. A drawing is either too complex or inadequate to provide insight into the problem. A problem involves 3-dimensional objects, and these will often coincide. A simple drawing is not good enough when you have to imagine things in 3-dimensional space, in which case, when they say use a model, they mean a literal figure model, an object, right? Get something physical and tangible, okay, and build and shape, right, either out of paper or wood or clay or something of that nature. And we'll return to the solution to the initial problem at the end of this chapter, which will unfortunately not be this video. Now there's something to prime your puzzler here, the Pythagorean puzzle. Here we have a scalene right triangle with legs of length A and B and hypotenuse length C, has squares drawn on its 3 sides as shown. If you wish, you can make a copy of this figure. I will center it on screen for you there. Right. Shade the squares, find the center of the squares by drawing in their diagonals, and label the intersection of the diagonals, and then erase, so you just have the center left. Using a protractor and a straight edge, you're going to divide the square into 4 pieces. And through this process, you can divide up these squares, cutting out the shaded regions, and you can physically check whether the areas of the squares, namely the sum of the smaller squares, is equal to the area of the large square. But I'll leave you to do that investigating on your own. Let's get on to the reading. All right. Knowledge of geometry is required in problems that involve perimeter, area, and volume. Perimeter involves measurement in 1 dimension. Area and volume, which we find by using linear measure, are important ideas in 2 and 3 dimensions, respectively. Sections 3.1 and 3.2 develop the notions of perimeter and area as applied to polygons and circles. In section 3.3, we use the concept of area to develop an important relationship between the sides of a right triangle. Then in sections 3.4 and 3.5, we apply ideas involving linear and area measures in 3 dimensions to find the surface area and volume of common 3-dimensional shapes. And this is, without a doubt, one of the most common and most practical applications of geometry and measurement. So, section 3.1, perimeter, circumference, and area of rectangles and triangles. An applied problem to get us started. A family plans to invest in new carpet for a living room. The floor plan and dimensions shown include a brick hearth and a hardwood entry, which will not be carpeted. If the carpet costs $22.50 per square yard, installed, and 5% extra area is allowed for cutting, how much will it cost to carpet the room? Okay. Again, a very practical application. People literally are doing this all the time. Buying new carpet, you need to know how much carpet. So here we have the dimensions, and you can pause here and try this yourself if you can figure out how much total area of carpet, right? Don't carpet the hearth and the entryway. We'll return to the answer to that at the end of the video. So the perimeter of a polygon. The perimeter of a polygon is the sum of the lengths of its sides. There's our definition there. Okay. Peri means around, and meter means measure, as we already know. Hence, perimeter literally means the measure around something. We can develop perimeter formulas for some common quadrilaterals. A square and a rhombus both have 4 congruent sides. If one side is of length s, then the perimeter of each of them can be represented by 4s. All right? So all that's doing is it's saying, hey, we know these shapes are consistent enough that we can find a pattern in every time I add up s plus s plus s plus s. Let's take a shortcut and call it 4s. And that's all of these formulas are. In rectangles and parallelograms, pairs of opposite sides are congruent. We will verify this formally in Chapter 5. Thus, if the lengths of its sides are a and b, then the perimeter of a rectangle or parallelogram is 2a plus 2b. We use a similar formula to find the perimeter of a kite. The following theorem summarizes these results. Now, remember, a theorem is a result that is proved or derived from other known facts or results. Okay? So you could build up a proof for this, and again, as mentioned, the book will do that in Chapter 5. So here's our rectangle, parallelogram, and kite, and we have summarized here all of the perimeter of quadrilateral formulas. Okay? Go ahead and write those down. We've got square, 4s, rectangle, 2a plus 2b, parallelogram, 2a plus 2b, a rhombus, 4s again, and a kite, 2a plus 2b. Here's a few examples. Okay. We've got find the perimeters of each of the following. We've got a triangle here, a square, some rectangle, notice all of the matching marks, so this is a rhombus. Okay. So just going off that first row, the perimeter of the triangle, we would add up the 3 measurements, 5 plus 9 plus 7, to get a total of 21 centimeters. The perimeter of the square in B is 4 times the side length 8, total of 32 feet. C, the rectangle, twice one side plus twice the other side, 9 and 5 millimeters respectively, gives us a total of 28 millimeters. And the rhombus here, that's perimeter 4 times 7, or 28 inches. Now the second row, E, F, and G, we've got a parallelogram. Here we've got a kite, the lengths are given. And this, these are marked as parallel, so that makes this a trapezoid. And we have all the measurements there. So for the parallelogram in E, once again, it's 2a plus 2b. Filling in our givens, we get 33.4 centimeters total. For the kite, 2a plus 2b again. Yes, they are dealing with fractions, so first go ahead and deal with doubling the fraction to get a total of 5 1/3 plus 12 2/5. You're going to need to look for a common denominator here to get a total of 17 11/15 of a yard. And finally, the trapezoid in G, we just have to add up all 4 lengths to get a total of 34.4 feet. Now, how about a circle? The perimeter of a circle, that is the distance around the circle, is called its circumference. Why? I'm not sure. We have a special name for the perimeter of a circle. Doesn't do anything different. Since ancient times, geometers have known that the ratio of the circumference to the diameter in any circle is a constant. In about 225 BC, Archimedes determined that this ratio was somewhere between 3 1071 and 3 1/7. That is, if capital C represents the circumference and D represents the diameter of any circle, then C over D can be approximated by 3 1/7 or 22/7. Okay? In decimal form, C over D is approximately 3.14. Where have you heard that before? Aha. Yes, indeed, the ratio C over D has come to be represented by the Greek letter pi, which has been determined to be an irrational number. That is, a non-terminating, non-repeating decimal. It goes on forever, new combinations of digits every time. So, irrational number, that is possibly a new vocabulary term. And we also will want the circumference, but we don't need to highlight this yet. It's coming up in a box for us. An approximation of pi more precise than 3.14 would be 3.14159.265. Goodness. By 2002, the value of pi had been calculated to more than 1 trillion places with the aid of a computer. Now, the definition of pi as C over D allows us to calculate the circumference of a circle. That is, because C over D equals pi, we can solve for C, right? We can write C equals pi times D, which would be equal to pi times 2r, or if you rearrange, because multiplication is commutative and associative like that, we can write that C equals 2 pi r, and that's probably the most common version. So here we have our postulate for the circumference of a circle, right? Remember, this is a postulate, not a theorem, because we are creating this definition, right? We have created the value for pi as defined by the ratio of C over D. Therefore, this we just have to accept will work, right? So C equals pi D, or C equals 2 pi r. So, for example, can you find the perimeter of each geometric figure seen here? The figure on top of the square is a semicircle. So first of all, in A, we have a full circle with, looks like this section is 5 inches and this is 5 inches. So that one radius is 5 inches. So the circumference equals 2 pi r, or 2 times pi times 5 inches, which would be 2 times 5 is 10. 10 pi inches total would be the exact solution, as it notes here, right? The exact answer is 10 pi. But to get a decimal approximation, which is usually more practical, we're going to round to 2 decimals here, 31.42 inches. And in B, we have a semicircle on top of a square. Square topped by a semicircle, or half of a circle. The distance around this figure is the sum of the lengths of 3 sides of the square plus half of the circumference of a circle. So the perimeter will be 3s plus 1/2 pi d. And we're using the d version here because this length given is the diameter of the circle. No sense dividing it by 2 if we're just going to have to double it again. So that, filling in our value of 7.4, we get 3 times 7.4 plus 1/2 pi times 7.4, or approximately 33.82 centimeters. And yes, you need to include the correct units. Okay, one level up from perimeter, we have area. We can use tessellations to determine the area of the region enclosed by a simple closed curve. For convenience, we use a square tessellation, where one of the small squares is taken to be our unit square. By counting the full squares and adjusting for all the partial squares, we can estimate the area of the region enclosed by the simple closed curve, shown in the figure, to be about 6 square units. Okay. This is an extremely useful process. So we set one thing to be our unit square, and then we count all of the full and partial squares to get an approximation. This seems rather simple, and it is, but believe it or not, this is a sophisticated geometry process. And you'll see greater and greater sophisticated versions in higher level mathematics. But they are based on this same simple process. Right? We can count like 1, 2, almost 3, this is almost 4, 5, and then a few scraps left over. Yeah, 6 square units. If smaller squares are used in the tessellation, such as 4 per unit square, as shown in figure B, then a better estimate of the area may be possible. Okay, notice that. If you use smaller squares, you can get a better estimate. This is the entire idea behind calculus. This discussion leads to our first area postulate. So the area of a region enclosed by any simple closed curve, for every simple closed curve and unit square, there is a positive real number that gives the number of unit squares and parts of unit squares that exactly tessellate the region enclosed by the simple closed curve. And B, the area of a region enclosed by a simple closed curve is the sum of the areas of the smaller regions into which the region can be subdivided. Okay. This sounds somewhat intuitive, right? This is saying that we can assign a number to the area of a figure based on the number of squares that fit inside it. And this one is saying we can find the area by adding up all of the pieces of area that compose it. Okay? Formally, this is important to establish ahead of time for the validity of later theorems. The real number described in postulate 3.2 is commonly called the area of the region enclosed by the simple closed curve. For example, if a region has an area of 2.3 square units, this means that the region can be covered exactly by an equivalent of 2.3 unit squares. There you have it. Why do we go to all that formality? Because we need a true formal definition of area. Okay? So use that as your definition of area. Oops. Okay. That leads us to area of a rectangle. Postulate 3.2 leads to some convenient formulas where we apply it to certain polygonal regions. Remember, a polygonal region is a subset of any enclosed simple region, or a simple closed curve. For example, suppose a 3 centimeter by 5 centimeter rectangle is covered by a square tessellation where the squares are 1 centimeter by 1 centimeter. We will always make this as convenient as possible. Since we have 3 rows of 5 squares, or exactly 15 square centimeters, that cover the rectangular region, we say that the area of the rectangular region is 15 square centimeters, which we can also write as 15 centimeters squared. Right? Don't forget the squared. Centimeters squared is a different unit than centimeters. When the length and width of a rectangle are whole numbers, as in figure 3.6, the area of the rectangular region, or area of the rectangle for short, is the product of its length and its width. Moreover, this relationship holds when the length and width of the rectangle are not necessarily whole numbers, but may be any real numbers. Aha. So here we have formally the definition for the area of a rectangle is the product of its length and its width. Please include the picture there to accompany your definition in your notes. Now, a square, of course, is a special rectangle where the length and width are the same. So, in case of a square with side length of s, its area is s times s, or s squared. Go ahead and add that one in the figure accompanying it here. Now, how about area of a triangle? Before finding the area of an arbitrary triangle, we will find the area of a right triangle. First, however, we will assume the following postulate. It essentially states that 2 triangles that are exact duplicates of each other have the same area. Again, it sounds like, well, duh, but for the sake of formalities that we will examine later, so that other definitions and theorems hold up to rigorous scrutiny, we need to establish all assumptions must be stated. Okay? Because we could encounter a strange geometric universe in which this is not true. So we want to make sure we've included this. Any 2 triangles whose corresponding angles and sides are congruent have the same area. So, using postulates 3.2 and 3.3, we can find the area of right triangle ABC in figure 3.8 by making a copy. We'll call it triangle A prime B prime C prime of triangle ABC, and arranging the 2 triangles to form a quadrilateral. So here's our original triangle ABC. We've copied and pasted, created the duplicate A prime B prime C prime here, and we're flipping it over upside down to land on top and combine together to form the quadrilateral there. Because the sum of the angle measures in a triangle is 180 degrees, we can show that all 4 angles of the quadrilateral are right angles. Hence, AC prime BC is a rectangle. Okay? We already know that it's got at least 2 right angles, and since these come from congruent triangles, you'll know that both these pairs will be complementary and thus also 90 degrees. Right? So according to postulate 3.2 and 3.3, because 2 identical right triangles make up rectangle AC prime BC, each of their areas must be half the area of AC prime BC. This leads to the following theorem. The area of a right triangle. The area of a right triangle is half the product of the lengths of its legs. So if we call the legs lengths A and B, then the area of the triangle is 1/2 A times B. So for example, determine the area of the following triangles. Here we have PQR and ABC, dimensions given. Because PQR is a right triangle, the area equals 1/2 7.4 times 4.3. equals 15.91 inches squared. Just multiply it out. Now, in B, we only know the formula for a right triangle right now. Don't get ahead of yourself. Both triangle ABC and triangle BCD, ABC and BCD, are right triangles. Thus, the area of triangle ABD is, I believe this should be ABD right there. That's what they're referring to, right? This smaller section, right, because you have the right angle there. This is a right angle, this is a right angle. I believe that should say ABD right now. So the ABD triangle would have its length 8 and 4, so 1/2, 8 times 4, 16 centimeters squared. And the area of triangle BCD, the small one here on the right, is 1/2, 3 times 4, or 6 centimeters squared. And thus, by postulate 3.2b, right, that said I can find the area of something by adding together the sub-areas, as it were, the area of triangle ABC is 16 plus 6, or 22 centimeters squared. Only there was a faster way to do that. Well, a line segment from a vertex of a triangle that is perpendicular to the opposite side of the triangle is called an altitude of the triangle. There's a fun vocabulary term, the altitude of a triangle. Okay? The length of an altitude is also referred to as the altitude or height to a particular side. Okay? So the length of the altitude is the altitude, or the height to the side. The side to which the altitude is drawn is called the base of a triangle associated with that altitude. So, in figure 3.9, that was this triangle up here, right? BD was the altitude to the base AC. In example 3.3b, we could have written the sum of the two areas as 1/2 8 times 4 plus 1/2 3 times 4. Factor, get 1/2 8 plus 3 times 4. This suggests the next theorem, whose verification is left for the problem set. The area of any triangle, not just a right triangle, the area of any triangle is half the product of the length of one side and the height to that side. You may have memorized the area of a triangle as 1/2 base times height. This is how we've established that, the base and the height being a side and an altitude drawn to that side. Height and base. Please include those in your notes, as well as the full theorem 3.3, complete with diagram. All right, let's try it on a few examples real quick. Calculate the area of these triangles in figure 3.11. We have a right triangle, some funky, tall, skinny triangle, and some really slanty triangle. What's going on here? Although the shapes of the three triangles are very different, each of the triangles has a base of 2 centimeters and a height of 3 centimeters. Even though this altitude is drawn outside of the triangle, it is still an altitude. It is a segment from a vertex of the triangle drawn down to perpendicular to the base, right? So even though we have to extend the line of the base to see where that intersection occurs, as long as you set that to make sure this is perpendicular, right, this will be 3 centimeters. So we have the same base. So that's all three triangles will have exactly the same area, 1/2 base times height, 2 times 3 times 1/2, or 3 centimeters square. We should emphasize that any side can serve as the base of a triangle when the area is to be determined. The base need not be the bottom side of a triangle. Okay? Any side is the base. Doesn't need to be the bottom. Because I can take my paper, and I can rotate it any direction I want. How about this one? calculate the area of triangle XYZ in figure 312. Well, let's see. We will use segment YZ as the base, where segment XW is the altitude of that base, because we're looking for where do I have a line from a vertex that is perpendicular to another side. So the area is 1/2 base times height, 1/2 6.9 times 5.3, or approximately 18.3 centimeters squared. Any triangle has 3 different altitudes or heights, 1 to each side. Good to know. The area of a triangle does not depend on which side and corresponding height are chosen. They all yield the same area. This would be a good figure to add as well. All right, and finally, converting units of area using dimensional analysis. In section 2.5, we use dimensional analysis to convert one unit of measure to another. We can use this technique to convert from one unit of area measure to another, as shown in the next example. Right? This will be very useful if we go back to that carpet problem from the beginning. Convert 10 square yards to square feet. And yes, even though the exponent comes after the unit name, I still look ahead and read this as, instead of yards squared, read it as square yards. So first notice that we are converting square units to square units. It makes no sense to convert square yards to linear feet, for example. It makes no sense to convert square to linear. Cannot be done. It is not a unit conversion. That would be part of a calculation. Okay? They're not equivalent otherwise. 1 square yard, or 1 YD2, can be represented as a square that measures 1 yard by 1 yard. There you go. Since 1 yard equals 3 feet, we can also view the 1 yard by 1 yard square as a 3 foot by 3 foot square. Okay? So now we have 3 feet by 3 feet. So thus 1 square yard equals 1 yard times 1 yard. Replace each yard with 3 feet. 3 feet times 3 feet is 9 feet square. Notice that in figure 314b, there are 9 square feet in the square yard. So to convert 10 square yards to square feet, we can write 10 yards squared equals, we will write it as a fraction over 1, 10 yards squared over 1, times 3 feet times 3 feet over 1 yard times 1 yard, because we know this is the unit conversion between yards to feet. You could also go directly between yards squared and feet squared and use 9 and 1 up here. It'll get you the same thing. But we started with yards. We want to get rid of yards, so we make sure the yard portion of this fraction is on the bottom. Its equivalent is 3 feet, so the yards now reduce, 2 of them, and there's 2 of them down there. So it's now 10 times 3 times 3 over 1 times 1 times 1 in the denominator, and the only units left are feet times feet, or feet squared, so a total of 90 square feet. In example 3.6, because 1 yard squared has 2 dimensions, we use the conversion factor 1 yard equals 3 feet twice to make the conversion, right? 2 dimensions, use the factor twice. We can also use dimensional analysis to convert between English and metric units of area, as shown in the next example. An Olympic-sized swimming pool of uniform depth measures 50 meters by 21 meters. What does that mean in American? The bottom of the pool is to be treated with a sealer, and 1 gallon of the sealer covers 300 square feet of surface. How many gallons of sealer will be required for the job? Recall that 1 inch equals 2.54 centimeters. Wait a minute, centimeters, inches, that's not even what we're going for. This is going to take a while. First, we must determine the area of the bottom of the pool in square feet. we can calculate the area and perform the conversion at the same time as follows. Because it's all multiplication. So if the area of the bottom of the pool, length times width, is 50 meters times 21 meters, so we're just using the dimensions given, but create that as a fraction over 1. So now we convert. I want to get rid of meters down to centimeters because that's my connection over to the English units. Meter on the bottom, centimeter up top. 100 centimeters in 1 meter. I have meters appear here twice, so meters must be here twice, centimeters twice. And now I can convert from centimeters to inches using that given conversion. Inches up top, centimeters on the bottom, so centimeters reduce. Use that conversion factor twice because we're in square units. And multiply by another fraction to convert from inches to feet. 1 foot contains 12 inches. Inches on the bottom so that they reduce, and all we're left with is feet. Make sure you use the linear conversion factor twice. So now all the units have reduced out except feet and feet or square feet. Multiply all the numerators and all the denominators together, and you will get approximately 11,302 square feet. And now we can use a final dimensional analysis again to determine the number of gallons of sealer needed, because we know, set that square feet as a fraction over 1, we know 1 gallon covered 300 square feet, so we'll write it as a fraction with the square feet on the bottom, gallons up top, feet squared reduces, and now multiply across and then do the division. The only unit left is gallons. 11,302 divided by 300 is approximately 38 gallons. Therefore, approximately 38 gallons of sealer would be needed. And we could go into, okay, if a gallon costs this many dollars, how much is the project going to cost? Keep going and on, so on. So how about that carpet problem? How did you do? The total area of the room, the whole room, right, is 18 by 22 or 396 square feet. The areas that will not be carpeted consists of 1, the entry, a simple 3 by 4 rectangle or 12 feet squared, and 2, the hearth, which has been divided here into 2 rectangles and 2 triangles. We'll zoom in on the picture, you can see that more clearly. Got 1 large rectangle up here, 1 itty bitty rectangle there, and 2 tiny triangles in the corners. So we've got 3 times 4 plus 2 times 1 plus 2 triangles, each 1/2, 1 by 1, for a total of 15 square feet in the hearth. Thus the area to be carpeted is 396 minus 12 minus 15, or 369 feet square. Taking into account the additional 5%, we're going to take 369 plus 5% of that, or 0.05 times 369. You get a total of 387.45 square feet must be ordered. You need a little bit of extra carpet so they have room to trim and cut all off the edges as they lay it. Okay. The total cost then at $22.50 per square yard is, so 387.45 square feet times yards to feet again, because it's square feet, so now we're down to yard times yard, and it's $22.50 per square yard, so this crosses out those and we're left only with dollars. Multiply across and then divide. $968.63. All right, and a final note, geometry all around us. Fun fact, in 1997, a U.S. flag created by Ski Dembski was listed in the Guinness Book of World Records as the largest flag in the world. This huge flag measured 255 feet by 505 feet, larger than 2 football fields. And it weighed 3,000 pounds. It has frequently been displayed at special events such as Super Bowls, World Series games, and NASCAR races. Unfurling the flag requires the coordinated work of 600 workers. Oh my goodness. There you go, perimeter and area of triangles and rectangles. Thank you very much. We'll see you in the next one.